Hello, and welcome to AP Chemistry Review 3.12, the photoelectric effect. In this video, we're going to talk about how photons of the electromagnetic spectrum can be absorbed by molecules or by atoms, causing different types of results. And this allows us to analyze what's going on in a molecule or an atom based on the type of radiation that they absorb. So the first thing I want to talk about is the electromagnetic spectrum. You'll notice that we're going to go from low energy on the right to high energy on the left. The types of electromagnetic radiation are radio waves, microwaves, infrared, visible, ultraviolet, X-rays, and gamma rays. Now, as you go from low energy to high energy, the frequencies increase. Low energy electromagnetic waves have low frequencies on the order of 10 to the third, and high energy electromagnetic waves have high frequencies on the order of 10 to the 24th. The opposite is true of wavelength. The wavelength actually decreases. It's an inverse relationship. So radio waves have very long wavelengths, and then they decrease as you go to gamma rays, which have very, very, very short wavelengths. So wavelength and frequency are inversely related. In fact, there's an equation to relate wavelength and frequency of a wave to one another. The equation that relates wavelength and frequency is the speed of light, which is a constant. We'll talk about that in just a second, equals the wavelength of the photon, the type of light we're talking about, times the frequency. And just a note about these symbols. This is the Greek letter lambda. It stands for wavelength. And this is the Greek letter nu, which stands for frequency. The unit for wavelength that we will conventionally use is meters. The unit for frequency we're typically going to use is hertz, and a hertz is exactly the same as an inverse second. C is the speed of light, which is 3.00 times 10 to the 8th meters per second. This equation, as well as the speed of light, will be given on your equation sheet, so you don't need to memorize them, but you do need to be familiar with what all these symbols mean and how to substitute. Notice that meters times the inverse seconds gives you meters per second, so the units work out, and that's why we use wavelength in meters and frequency in hertz. So if we're given wavelength, we can calculate the frequency, or if we're given frequency, we can calculate wavelength using this equation. So what do these different types of electromagnetic radiation do to molecules? Well, they cause different types of behaviors. If a molecule is hit by a microwave, microwaves have enough energy to cause molecules typically to have rotational energy. So if a microwave hits a molecule with the right amount of energy, the molecule will actually start rotating. And the amount of energy in that rotation will exactly correspond to the energy that the photon had. So if a photon has X amount of energy, then the molecule will start rotating with X amount of energy. They have to be correlated, and that's the photoelectric effect. So microwaves cause rotational energy. This is the way we heat food in microwave ovens. As microwaves hit the water molecules in your food, the water molecules start vibrating, which translates into heat, and that will cause the molecules, your food, to heat up. Infrared causes vibrational energy in the molecules. So when infrared hits a bond, like the double bond in this oxygen molecule or the double bond in this carbon dioxide molecule, it'll cause those bonds to vibrate with the exact same amount of energy that the photon had. Now, they won't start vibrating with any photon. The photon's energy has to match the vibrational energy of the molecule itself. This is one way we can analyze an unknown substance, is by bombarding it with infrared energy and seeing what specific energy is absorbed and what type of bond corresponds to that energy. It's very, very interesting, and you'll hear more about that in another video. So when molecules are hit by microwave or infrared, we get either rotational or vibrational energy. When atoms are hit with higher energies, such as ultraviolet, the electrons can actually transition from low energy levels to high energy levels within the atom itself. So I'm going to scroll up here. And here's a Bohr model of a hydrogen atom. Now, I used the Bohr model just for simplicity's sake, so we can draw this very easily. But do realize that there are not actually rings in the atom. You actually have inner orbitals, sp, d, and f orbitals, where electrons have a probability of being located. But we're going to use the Bohr model just for simplicity in talking about electron transitions. So when a photon hits an electron in an atom, if that photon has the same energy as the jump between two energy levels in an atom, and remember, these energy levels have fixed energy, then that photon will be absorbed by the electron. The electron will jump to a higher energy level, and it will now be in an excited state. It will no longer be in that lower energy level called the ground state. It'll jump to a higher energy level called an excited state. That energy is exactly the same. That transition energy is exactly the same as the photon that hit it. Now, again, not any photon will do this. It has to be a photon with the energy that corresponds to that jump. The same is true when an electron goes from a higher energy level back down to the ground state. When it jumps back down because it's unstable, the electron will actually release a photon, and that photon will have the exact same energy that the transition between the high energy and low energy has. So again, we can know how much energy there is between two energy levels in an atom because the photons that are released by that atom correspond to the jump between energy levels in that atom. And again, this is the photoelectric effect. The idea that the energy of the movement in an atom corresponds to the energy of a photon released or absorbed by that atom. So how can we calculate that energy? Well, we're going to just go back up here. I'm going to give you an example, and let's see what you come up with. So let's say that you have a wave that is 15.8 meters long. Okay, so that's its wavelength. And we want to know what its energy is. So how much energy does this photon have? So we're going to calculate this by using an equation that you haven't seen yet. And that equation is the energy of a photon equals Planck's constant, which of course is a constant, and I'll tell you more about that in a second, times the frequency of the photon. Planck's constant comes from the ratio between the energy of a photon and its frequency. It turns out that the ratio between the energy of a photon and its frequency is always exactly the same. It's called Planck's constant. And Planck's constant is 6.626 times 10 to the negative 34 joules seconds. Joules, because that's the unit of energy, and seconds, because seconds will cancel out the unit of hertz, which is on frequency, because hertz times seconds they cancel each other out. That'll leave us with joules, which is the energy unit we need. So to calculate the energy of this photon with a wavelength of 15.8 meters, we first need to know what the frequency is. Notice I gave you the wavelength. So we need to go back here and calculate the frequency using the equation that I gave you earlier. So let's go ahead and do that. Speed of light is 3.00 times 10 to the 8th meters per second. The wavelength is 15.8 meters, and we're calculating the frequency. So we just need to rearrange this equation, divide the speed of light by 15.8. So 3 times 10 to the 8th divided by 15.8 gives us, and it didn't give it to me in scientific notation, 367. So that's 1.90 times 10 to the 7th hertz. Now I'm going to leave the entire number on my calculator. It's a much longer number, more decimals. I'm going to leave that on my calculator and round at the end, but just for simplicity here, I'm rounding right here. So we have the frequency now. Now to calculate the energy, we just need to plug the frequency in to the equation. So the energy of a photon equals the wavelength. So the Planck's constant, 6.626 times 10 to the 34th, negative 34th, joule seconds, times the frequency, 1.90 times 10 to the 7th hertz. And so if we multiply those two together, and I'm going to, again, use the entire frequency on my calculator. So the entire frequency times 6.626 times 10 to the negative 34th. If we do that, we get the energy of this photon to be 1.26, rounding for 3 significant digits, times 10 to the negative 26 joules. And so that's how much energy one photon of this light has. 1.26 times 10 to the 26. We can look on our chart here and see where on the electromagnetic spectrum this would exist. So 15.8, that would be times 10 to the 0. So somewhere right, or 10 to the 1. So that'd be right in here in the radio wave. So this is a radio wave, very low energy radio wave. So that's the photoelectric effect. Again, for how this is used in spectroscopy, you'll need to watch another video. Good luck with your studying. Bye-bye.